Great, thanks, Athena. Good afternoon or good morning, everyone, depending, I guess, on which time zone you're in. I'm James Ricci, and along with Mo Abu Ali here from IoTco, we're going to be talking about Industry 4.0. So what we plan to do is, over the next hour, is to provide a pretty detailed look at Industry 4.0 with a framework to really implement it, but also some case studies from die casting specifically, kind of demonstrating that operational benefit. And in this case, we're going to talk about it as it relates to maintenance and quality. Now, for those of you who are less familiar with Industry 4.0, I'll provide an overview as part of my section on these challenges and opportunities associated with it. And Mo is going to lead sort of the case study examples, and then we're going to wrap up with Q&A. Now, before diving in, though, we'd like to give you a little background on our companies and who we are specifically and kind of why we're doing this NADCA webinar. So for those of you, I'm James Ricci from Harbor Results. I'm actually the Chief Technology Officer for the company. I have about 25 plus years in manufacturing with a background in engineering, quality, and operations. And as it kind of states here right on this slide, Harbor is all about performance improvement and doing more with the same or less, in fact. And so we've been working with NADCA and, quite frankly, many other associations and companies on this concept, but more specifically for NADCA, we've been, over the last few years, working with NADCA members to provide a lot of benchmarking data and identify improvement opportunities for your business overall, and then providing kind of recommendations to do that. And in some cases, this includes business assessments. This includes just straight benchmarking survey analysis, but it also includes things like these webinars that we're doing today. So that's a little bit about Harbor, and I want to give Mo a minute to talk a little bit about IoTco. Mo?
Yeah, James, thank you very much. I appreciate the opportunity to present with you. My name is Mo, and I'm a managing partner with IoTco. Been in the industry for about 22 years, and worked in the automotive industry in Toyota, and then worked in the software industry serving manufacturing. IoTco, we are the Internet of Things company, and we're a partner of Harbor. We provide 3 lines of services or practices. So we're very focused on predictive maintenance and predictive quality. So overall, how to use predictive analytics in a variety of industries, including die casting. And to complement predictive analytics, we offer training around digital transformation and IoT, as well as turnkey solutions for instrumentation and automation of plant floor equipment. So we primarily work in the automotive and the aerospace industry, and again, it's a pleasure to be here today to present together with Harbor. Thank you, James.
Thanks, Mo. So let's kind of start getting into the meat of the webinar. For starters, though, I don't want to dive into too much details right away. I'd like to kind of level set everyone on what we mean by Industry 4.0. First of all, it's all about combining kind of what we do in manufacturing day in and day out, but then kind of leveraging the technology that's all around us, especially those technologies that are designed specifically for industrial type of applications. So in this case, you have machine-to-machine interfaces, Internet of Things applications, and they're all targeted toward making it easier to automate, speed communication, monitor operations, and quite frankly, self-correct when something happens or goes wrong. And this whole self-diagnosing, self-correcting function is where you get that quote-unquote smart term from. And so you end up with this situation where you have smart equipment that can communicate with other smart equipment, but then quite frankly, it can also communicate with people. So interesting, Industry 4.0, but so kind of, what does it do? What does it provide? Why does it matter? And quite frankly, it provides a lot of the same benefits that everybody in manufacturing is working on every day today, right? Pricing pressure, lead time, productivity, you name it. And so I have a couple things highlighted here in italics that I want to bring to your attention. And one of those there is at the top is this smoother processes to free up workers. And then the more toward the bottom there, we have slowing or changing demand. And that demand can be changing up or down. And from our perspective at Harbor, it's pretty important these days to be able to, in the current business environment and the current unemployment numbers and the ability to identify skilled trades, to really focus on things that allow you to adapt to changes in demand and allow you to take the scarce resources sometimes that we have from a labor perspective and free them up for higher quality, higher value added tasks. And so the other piece of this is, so when you think about Industry 4.0 and how this applies to you, it applies to you. It's not this, maybe this big automotive OEM thing, like it's not a GM, this isn't only for GM or Boeing or a really huge company. It's really for everybody. And when you think about US and North American manufacturing, the fact is manufacturing dominated by small and medium-sized firms. In fact, about 95% of all manufacturing companies in the United States have fewer than 100 people, or give or take, if you want a ballpark number, call it around $25 million in revenue. And so, you know, this is pretty common, not just for the US, but really, quite frankly, throughout Europe, and in Canada and other developed countries. So this isn't something that's just unique to the US. And so Industry 4.0 is for everybody, not just sort of that 1% big company that's out on the far right of this chart. So further to this point, so why do we want to talk about Industry 4.0 today and some of these things that Mo is going to talk about in the case study? And it really stems a lot from Harbor recently surveyed a wide swath of manufacturers on both software and technology. And some of the results you're seeing on this chart. And what you're seeing is there's a lot of industry standard tools out there, like a ERP software, enterprise resource planning software, that have really, really high implementation rates. So if you look at the far left of this chart, you look and you see a green line. And that green line under ERP software is right around just north of 90%. So what that's telling us is the groups that we've surveyed, the manufacturers we've surveyed, more than 90% have implemented an ERP software. And 86%, that big sort of reddish orange bar, are yielding positive benefits from that implementation. So what you see as you start to scan left to right is that the implementation percentage drops off pretty drastically, and so do the benefits. And then when you look at these last four, these items have a direct tie to Industry 4.0, but what you're seeing here is incredibly low adoption rates and limited benefits. And so we had asked some questions around, you know, what's the time horizon that you think some of these tools are going to be implemented and start receiving benefits? And what we found was that a full 30% of the people that we spoke with and surveyed and researched said that implementation on these four tools to the right were more than 10 years away. And another group viewed it, you know, almost 5 years out. But the interesting thing here is Mo's going to show you here shortly some case studies where implementation and the corresponding benefits are already here and in the die casting industry. So we want to make sure that we're clear that the benefits can be accrued today, despite the fact that a lot of companies don't feel like they're receiving them. But as the old adage goes, right? Time, money, and resources. You can have two. You can't have all three, right? So where do we focus? Our scarce resources and our meaningful time. Where do we go to get the greatest benefit? And for that, we said, okay, how can we look at Industry 4.0, and how should we do this so that we can capture the benefits given the constraints we have in our business? And so what Harvard did is we went and created a roadmap to kind of help with the implementation. So there's a lot to take in on this slide here, so just give me a second. So our roadmap, as we look at for Industry 4.0, spans 6 levels, literally level 0 to level 5. And we include this nomenclature of basically no implementation, no automation at level 0, all the way to a full implementation at level 5. Okay? And as you go from left to right, the reliance on human intervention decreases proportionally from left to right, whereas the reliance on automation and technology increases, okay? Now, the other piece of this, though, that we want to take a look at is this continuum is evaluated against people, process, and technology. So when we're talking about Industry 4.0, we're not just going to talk about some new, really cool piece of die casting equipment. We were going to talk about it more broadly than that. And what I'd like to do is I'd like to explain each of these in some level of detail and going through each one of these. But the thing I want you to understand is your benefits to Industry and Industry 4.0 roadmap and implementation is only as far as your weakest link. So in other words, if you could have the greatest equipment in the world and world-class processes, but if all your people aren't trained on how to use it and don't follow the processes, then your benefits are only going to accrue to the bottleneck, which is this orange bar, which is the people section. So we're going to walk through each of these and talk about some implementation challenges and opportunities associated with these. So let's start with kind of the most fun one first, which is, technology. So despite the fact that I told you that it's not all about technology, it tends to be the one that's the most fun. So, and this is really, from a technology perspective, this is your transition from sort of this analog manual world to a digitally connected manufacturing shop floor with cross-functional automated manufacturing cells. So that's really the full gambit of what you'll see. But what I want to talk about as it relates to technology, I want to talk about it more broadly. I want to talk about technology as it relates to automation, connectivity, and intelligence. And what I want you to imagine instead is technology, instead of thinking about it from an equipment perspective, I want to think about it from a human body perspective, okay? So automation, that's your muscles. Connectivity would be your nervous system, and intelligence would be your brain, okay? And so automation is what you use to be flexible, right? You need to react to what's going on. That's exactly what your muscles do in your body. So this basically is, automation is helping you make sure you meet your customers' needs without having to completely blow up your shop floor or all your processes of what you do. Connectivity, or your nervous system, right? That's about how all these devices and your systems are connected together. So you're going from this hardwired analog world to this wireless digital world, and all the communication paths and all the protocols that go along with managing that. So this is really your IT system, but it's not your IT system that's about running wires and keeping servers backed up. It's much broader than that. And then we have intelligence, or your brain. And this is this idea of, we want to operate faster in a data-driven and intelligent way to basically improve our business. If we're going to implement all this stuff and we're not going to improve our business, then there was really no point in implementing the system, quite frankly. So we look at all this stuff. So when we talk about automation, connectivity, and intelligence, what are the tools of the trade we're talking about? We're talking about everything that you work with every day right now. Could be CNC machines, it's die casting machines, it's robots, it's cobots, it's your ERP system, it's your shop monitoring systems. It's all of these tools, right? And we also have givens that we have to think about around connectivity, your cybersecurity, those things, which in reality, when you really start looking at it, those are anything but givens. There's a lot that goes on in setting all of that up from an Industry 4.0 perspective. So technology, we've got all these tools, and technology, whether it's software or other pieces of equipment or this automation we're talking about, it needs a process around it so it can be leveraged. And ideally, your processes match your technology, right? So that you can get maximum value and kind of move from left to right on this scale. And so what we see today, and we're in and out of manufacturing plants, myself and Mo, all the time, whether it's due to a combination of poor planning, broken systems, lack of technology use, human capabilities, a lot of plants are operating in a very reactive short-term basis today. They're very much focused on just what do I need to get done today? And kind of every day ends up being a little bit like Groundhog Day. We come back in, we fight the same fires and the same battles, and we walk out the door on Monday, and we come back on Tuesday, and we do it all over again, right? Everyone wants to be further to the right on this scale, right? We kind of, a lot of people we talk to, they often see predictive as pretty far off, in this concept of real-time self-optimizing as some absolute blue sky nirvana, you know, despite the fact that there's many manufacturers out there doing this today. So from a process perspective, what we need to think about is, you know, how do we leverage that brain, right? How do we move left to right on this scale? And as you move from left to right, you are able to extract a significant competitive advantage. And so when you look at this table, what we need to think about is we need to consider how the processes that we're using to manage the business day to day, how do we move from reactive to proactive? But more importantly, how can we move to being actionable, okay? And ultimately, actionable is telling you what you need right now to make the best decision possible. And to do that, you need good, reliable data. So what do we mean by data? How do we get, if we're going to get actionable on data and through Industry 4.0, we have to think about data in a slightly different manner. And so we call it like the 5 V's. Okay, so you can see them across here: variety, volume, velocity, veracity, and value. And what we find is we end up in a situation where a lot of shops sort of first begin to talk about the variety of data available and the volume. We tend not to really talk about the velocity of data. It's sort of just assumed, right? You know, that report runs every night, James, or this thing updates every hour or whatever. And it's sort of velocity is just assumed on how this works. The interesting thing we get stuck on is a lot of times is when we get to veracity and value, we end up debating these to the point where we can't even make a decision on the data anymore, right? So we can't get actionable. So what do we do instead? We kind of revert back to our gut instinct, right? I mean, there might be a couple plant managers on this webinar. I know I've been in this situation as a manufacturing manager. It's like, hey, I've seen this before. We just need to do this. And sometimes you're right, but a lot of times you're not. So how can we get more actionable? So what can we do? And my recommendation to you, and this will tie into what Mo's going to cover here shortly, is let's get actionable by datafying your business. And so what do we mean by that? Okay. What we mean by that is find something that's important to you. Pick a data stream that's important to you and automate it. Okay. So automate the data acquisition, the data transportation, and the data analysis. Okay. So data acquisition, that's all your sensors and all the devices that are coming off all of your equipment that you can capture today. Transportation is how does that information move through your system? You don't want it to be captured manually, like let's capture our downtime manually and then someone's going to go enter it into an Excel spreadsheet somewhere. But we want to automatically capture this information, and we actually want that to feed our analysis tool. And what do I mean by an analysis tool? This is could be a BI dashboard like Tableau or Power BI, but this is this whole concept of big data. It all feeds into a system, and then it's analyzed and presented to us so that it's actionable. And so what we want to do is move away from this idea of debating and tracking data for tracking's sake, and we really want to focus on information that's going to improve our business. And so ultimately, picking a data stream, pick something that it's important and useful for you, and it'll be important and useful to everybody else, and it will drive decision making. So what we want to do is we want to take our processes, and again, we want to match up our data and information with this. So we want to move from being reactive to proactive. Now, last piece of this puzzle here for Industry 4.0 on this roadmap, quite frankly, is people. And people are really the biggest wild card in an Industry 4.0 implementation. And so, technology, you can generally get your hands wrapped around, right? You can buy certain things. It's a CapEx plan to kind of pull this together. Process, it's a little more difficult, right? You're changing some processes and systems, and you're bringing data in, and then there's a lot that goes with that. And it becomes people we find are ultimately inextricably linked to both the discipline of the process and the success of the technology implementation. And so I'm going to keep one of my last slides here. I'm going to kind of keep this simple because, as I'm sure you know, that this transition from a world of limited reliance on or full reliance on people to limited reliance or dispatching on people, this change, this fundamentally alters people's roles and responsibilities in an organization. And it also creates a need for many new competencies in your organization. So not only do we have people's roles changing, but actually we have new skill sets that are required to be successful. And so we end up in a situation where we have to recognize that your role as a leader is to understand that technology changes exponentially. It changes really fast. People and organizations don't. They change more logarithmically. And what you end up with is a lot of implementation risk in the middle between what the technology can do and what the people in the organizations are capable of absorbing. And so your role as a leader in your organization is to manage through this transition. And so the best example I could give you, we were in the office the other day, think to something like Uber or Lyft, and think 10 years ago to 2008 and 2009. We weren't talking about Uber and Lyft in any meaningful manner, this concept of ride hailing. And today, it's ubiquitous. And so that's what goes on in this world. And that's a very simplistic example of what goes on. But that's the type of change that's going to begin to filter into the manufacturing industry. And so this isn't something, as I referenced before, this isn't a 10+ year scenario. 10+ years, it's going to look very different than it's looking today. So what we want to do is I'm going to turn this over to Mo. And what we'd like to do is kind of get real with some of the case studies within die casting that Mo can walk you through to kind of see how this works today and in the real world. And with that, Mo, I'm going to turn it over to you.
Thank you, James. Thank you very much. So technology, process, and people. What I'd like to do, with the audience here is go through a case study of technology deployment in the die casting industry, and also describe, how the people element is engaged to use the data from the predictive tool and to support, their different roles within the organization. But let me start on a higher level, just to paint the picture. So obviously, the field of IoT is not a new field, right? And Industry 4.0, as very well described by James, is an initiative that supports organizations to embrace IoT, and specifically in our industry, the industrial IoT, industrial Internet of Things, which is in the manufacturing operation, right? So as an organization, we at IoTco, we are very focused on bringing digital transformation success stories to the casting industry and many other, manufacturing verticals. And when we go into a manufacturing operation, from the technology perspective, we like to assess the digital maturity of the organization, right? So we look at the machine layer. We get an understanding of, the PLCs and the CNCs and the level of connectivity on the plant floor, right? We take a look at SCADA systems, the data acquisition layer within the manufacturing operation. We also assess if there is an execution system that is being connected on the plant floor, collecting the data. And we sometimes look at the ERP layer as well. Is your organization doing maintenance today using, for example, a maintenance module within your ERP system, right? So as James alluded to, tools of the trade, right? So what is a digital maturity, and what are the tools of the trade, and how well they are being used to drive, digitalization in your operation? And once we do get that understanding, we're able to clearly map out 4 different points, or 4 different pillars of a digital transformation strategy, prior to deployment of an advanced solution within the casting industry, for example. And we start with number 4 and we count backwards, right? 4, 3, 2, 1. So what is the ROI? What is the problem definition? What type of issues do I have in my casting process, right? Is it the casting cell itself, or is it maintenance related, or is it uptime related, or is it quality related? And I'll show you an example where we're doing what's called predictive quality on a casting cell, because I think most of the folks on the call, you do understand that the average quality, scrap rate in the casting industry could be anywhere from 4 to 8%, right? So how do you reduce that? And once we understand the problem definition, we're able then to strategize on, what is the level of connectivity, and how do we connect the plant floor to get the right information? And then how could that information, or the datification that James mentioned, how could that data be used to drive analytics on the plant floor, okay? And how those analytics could then be scaled across the organization. And then obviously there's a technology aspect of scaling that technology, using templates or using variety of approaches across the manufacturing plant. So we like to understand, what is the role of digital transformation within your organization. And once that understanding is in place, we drive hard on the business case. So if you look at the left side of the screen, and I think this applies more to the folks on the call today, but if we look within the manufacturing plant or the smart factory applications that we do every day, there is several use cases. So obviously, the more prevalent use case is how to use predictive maintenance to drive improvements of uptime and to even sustain high levels of uptime in a manufacturing facility, right? So obviously, uptime is part of the OEE calculation, your overall equipment effectiveness, assuming that metric is being used and measured in the factory. And once predictive maintenance is applied and being utilized, not only would it drive improvement in uptime, but it could also impact the spare part management within the organization. I mean, moving away from a fail and fix approach to a predict and prevent approach of running your facilities could impact and lead to reductions in spare part in the plant, because if there is accurate predictions to the future, then predictive replenishment of the spare parts can actually occur while keeping a lower value of spare parts within the factory, right? This is a use case we quite often do. Another use case, which I'll describe in detail, which also is now being widely deployed in our casting clients, is predictive quality. And this is where we have the capability to use advanced analytics, including artificial intelligence and machine learning, to actually predict aluminum scrap or casting scrap on die casting machines, and to do that with a high accuracy of prediction in order to reduce that 4 to 8%, standard scrap rates in the facility dramatically, right? And it all depends on the maturity within the organization. It is a phased approach. I mean, connectivity leads to predictive maintenance, which leads to predictive quality, and which would lead to overall process optimization. Okay. I mean, there are clients who have a high level of maturity where they can achieve that, level 4 or level 5 in the Industry 4.0 roadmap that James showed, which would allow them to use AI to actually feed data back to the process, okay? To feed data back to the robotics or to the casting machine, and to actually, make prescriptive decisions, actionable decisions, real-time decisions on the asset without human intervention, okay? And I'll also describe how we do that today in the casting industry. So keep the business case in mind. The message is always keep the business case in mind, and the business case drives the technology adoption. So I want to show a quick ROI, more predictive maintenance related. So we do a lot of work in the automotive OEM space, and one of the earlier case studies that we first did within our organization was on predictive maintenance of a robotic facility. And the automotive OEM at the time had a large facility of robotics, and just 1 minute of downtime in a robotic facility was a very significant number. Okay, $10,000 of downtime. That number I think has recently increased because obviously you're not making cars, right? If a robotic is down, the lines are impacted, and therefore cars are not rolling off your line. So the using predictive analytics to capture robotic failures, and keeping in mind that robots do not fail all the time, right? They in fact only had 30 robotic failures per year on average, okay, out of 500 robotics. However, a single robot failure, leads to 30 minutes, up to 30 minutes of downtime, which is a severe downtime at an automotive facility, which crunching the numbers equates to $300,000 of worth one robotic failure of downtime in the machine or in the plant. And therefore, going back, if we use predictive analytics and only predict a realistic 50% of those failures, so 15 of 30 failures that occur per year, predictive analytics, has led and did lead to a significant ROI within that facility. And again, I'm not saying your 1 minute of downtime in your plant is $10,000, but your 1 minute of downtime has a number behind it. And just using such a simple ROI calculation to justify a predictive maintenance application in a facility would actually, deliver a significant ROI of typically less than 12 months within a manufacturing facility, right? So the realization now of using predictive maintenance on the manufacturing floor comes, via Predictronics. Okay, so there is a product out there that does that. I'm not here to talk about the product, but I'm here to talk about the use cases that drive the product. There are two critical use cases, and I want to explain that from the perspective of casting. I want to start first with predictive maintenance and then predictive quality. Predictive maintenance is very focused on the machine, okay? So by collecting sensory data, controller data, and other relevant information from the asset, using machine learning and AI, that information can be converted into 3 simple metrics, okay, for any maintenance or process engineer to use in their daily lives. The first metric is asset health, okay? The true health of that machine, just like the human body. You go to a doctor, you measure your pressure, your temperature, your heart rate, and the doctor is able to diagnose whether you are healthy or if there may be health issues. Same goes for a machine, right? There are specific parameters that are captured, say in the casting process, and by creating a baseline of what a healthy machine is and trending that data over time, we're able to find out what is the true health of that machine. Once we understand the health of the machine and start to trend the drift away from the baseline, we're able to calculate what's called the remaining useful life of that asset. That is a prediction, an accurate prediction of how many days or cycles are left until that asset may reach a failure mode, okay? And this leads to diagnostics. Diagnostics is the root cause of which component within that asset or which process parameter is leading to the failure, okay? So is it the dosing furnace in my cell? Is it the robotic? Is it the trim press? And what is the reason? What is the process parameter that is impacting that failure? So that's predictive maintenance. It is focusing on the machine. Then you have predictive quality. So in the casting industry, some of the newer advanced casting machines, you know, they come ready with automated quality inspection equipment. For example, there's a vision camera on the machine taking a picture or an X-ray of the casted part coming off the machine, right? In unfortunate situations, sometimes there are porosity issues, for example, on the casting, and that part still goes away or out of the foundry into machining or into, you know, future steps, and, you know, it is not caught from a quality perspective as a scrap. So how do we use predictive analytics and AI to correlate the machine parameters of the casting process, for example, to the quality parameters of the scrap types that are happening on the machine, and to predict in a very accurate way if a bad cast is going to be produced on the machine in the foundry in the beginning of the process before that part becomes extremely expensive and goes down the value stream. Okay, that is the idea here behind predictive quality, which is something we're doing quite successfully in the casting industry and other industries. At the end of the day, you know, manufacturers want a worry-free process. Okay, worry-free maintenance, worry-free quality, near zero downtime, and near zero defect rate. This is the vision that manufacturers would like to achieve using AI and machine learning, and again, keeping in mind the business case that they have to meet to justify the investments. I want to give a simple example on predictive maintenance just to paint the picture, okay? Again, you know, James mentioned people, okay? You know, these are advanced solutions. They're advanced analytics, advanced mathematics and statistics happening behind the scene. But the people using those technologies, you know, they are not PhDs, they are not data scientists, they are maintenance people, they are process engineers. They understand manufacturing, okay? So they must be presented with useful information in a very intuitive way that they can read it without, you know, requiring an advanced degree to work with such systems, right? And then they obviously have to trust in the data and use the data. So what you're seeing here is a machine, okay? And this is actually a robot on a casting cell. So the cell is a large cell by a Swiss company, and the cell includes an ABB robot. And this is, you know, one of the templates that is deployed on the cell, not for the casting machine in this case, but for the robotic on the casting machine. And what you're seeing is the true health of the asset, okay? So there's a lot of data being collected, and I'll explain that, and that AI and machine learning is used to create a baseline and then convert that data into the machine health, as I mentioned. So each one of those green points is your machine health, and then down here is your baseline. Yellow is your warning zone, and red is a failure threshold. And those are statistically learned from the model. So there's an obvious trend of degradation here. And before the machine failed, it hit warning, and there was a clear prediction window, which gave a 2 to 3 week window in advance for the maintenance person to actually act. And, you know, different decisions can be done here. You know, alerts can be sent prior to the fact of failure. You know, engagement with the maintenance system to replenish and use spare part for the robotic before the machine actually fails, right? So again, moving away from fail and fix to a predict and prevent approach to doing the maintenance operation. And in addition to that, a simple diagnosis of the specific component within the machine, or in this case, the robotic, that may be failing. In this case, axis number 5 on the robotic is nearing failure. You know, in most PM cycles today, a maintenance person may actually go to the robotic and they would change all the 6 joints, all the 6 bearings on the 6 joints. But with a tool like this, they can intuitively see that there's only one specific joint that needs to be replaced. So, significant reduction in maintenance time because only one joint needs to be fixed. And also to mitigate the early replacement of good parts, right? One of the hidden evils in maintenance today is parts are being replaced early, and those parts still have life to continue to be used in the machine, right? And that's a good example of that. So driving now away from predictive maintenance into predictive quality, in addition to monitoring the casting parameters and the components on the cell and, predicting maintenance issues, one of the biggest business case, maybe even the holy grail in the casting industry today, is how to reduce scrap rates, okay? This is a use case from a die-cast client that we've been working with for quite a while. And, their average aluminum casting rates or scrap rates is around 3.5%. I mean, I personally hear and I see studies where the industry rates are anywhere from 4 to 8, sometimes 10% in some of our clients, right? So in a typical lot size of 160,000 parts that they make in one product, okay, and on a typical machine, sometimes they make 3 or 4 products. It's 160,000 part lot size. So on average, 5,600 parts, that is 3.5%, are actually scrapped, okay? The issue is, if those parts are caught in the foundry, it's only $3.8 per part. But if those parts start to go down the value stream into machining, their cost becomes $11 per part. When they go into assembly, it becomes $28 per part. When they go to the customer, it's priceless. There's traceability issues, warranty issues, recall issues, ... fill in the blank, right? So the cost of scrap is lowest to the client in the foundry level with the machining cells, the die-cast cells that are operating in the foundry. So we conducted an extensive project of using predictive analytics and specific predictive quality in this die-cast manufacturer here, using one of our AI templates. And the idea was how to detect scrap early and how to predict scrap early on the cell with an average savings that was communicated and validated at the client of almost anywhere between 70 to 135K per product per machine, okay? So moving on, predictive quality, obviously to deploy predictive quality, now we understand the business case, but now comes the deployment, right? So if you look at a high pressure die cast cell, and here's an example, the project that we did was with a company called Bühler in Switzerland. So they're the OEM of the machine, and it was die cast cell. It was a Carat 220, which is one of the newer die cast cells that Bühler makes in Switzerland. I mean, these are the critical areas of the die casting cell, okay? And data collection has to be set up, right? Again, datification. We need to datify the cell. We need to obtain or to create a standard data lake, as we call, and this data lake should have high quality data attributes that are collected from the critical areas of the casting cell, okay? And the cell has a Siemens S7 controller. I mean, it has the capability to provide us that data, okay? And you see here some of those critical areas include obviously the casting cell itself, including the dosing furnace, including the robot where I showed you the predictive maintenance example, and the trim press and other critical areas, right? So we strategized on creating that standard data collection layer. And on the right here, you see that we set up a standard communication protocol using OPC, where we were capturing data from the cell and from other critical equipment on the cell, including camera information, okay, that was actually readily available on the cell, which provided us data on the scrap or the good parts on the machine, which allowed us to train the models for predictive quality, right? So this data collection architecture here became a standard architecture that, you know, was deployed in the first factory, but it was also rolled out in, you know, 10 additional factories using this standard data collection template. Okay. So moving on, this is the predictive quality template that was deployed at the client, right? So we talked about data collection. So there is a series of mathematical or machine learning algorithms that are deployed, okay, through PDX, the solution, where we're able to analyze that signal information, make meaning of that data, convert that data into statistics, which are called features, and those features are used to train the health assessment model that indicates the true health of the machine and also the health of the part that you are producing. Because keep in mind, there are two data sets. There's the machine data and there's the quality data that are obtained real time from the machine into the data lake. Once the baseline models are deployed, and we need about 2 to 4 weeks of baseline data, that baseline is then used to start creating predictions over time. And again, depending on the components of within the machine and the type of parts, there are two predictions. There is the machine predictions for, let's say, the robotic on the cell, and then there is the quality predictions if a good part or a bad part is being produced on the cell, right? And then you have diagnosis, right? Diagnosing the root cause failure on the machine, as well as diagnosing what could be the quality defect on the part. You know, is it a porosity issue, or what type of issue is actually on the part? So this 6-step process here becomes a template. This template is deployed successfully for, you know, 1 to 2 cells, high pressure die cast cells, and then they could be used to roll out an additional 10, you know, 100 cells over 10 manufacturing facilities, assuming the cells have similarities to each other, and then the rollout of the analytics solution can be done in a streamlined and in a rapid way using this template approach. Okay, but this is the recipe. That's what's happening behind the scenes. So if we go briefly a little bit deeper, I'm going to show 3 steps. The first step is specifically what data was collected. Okay, so in fact, over 80 data parameters were collected. I give you an example on the cell itself. You know, we looked at the pressure of the accumulator, the pressure of the ejector, and the pressure of the squeeze pin. And if you guys are familiar with the squeeze pins on the casting machines, I mean, those are tiny components, but those components could actually, you know, lead to potential hazardous issues and scrap issues on the machine. So we actually had a specific template for the squeeze pin predicting issues on the squeeze pin itself. And we are actually feeding data back to the Siemens controller on the machine and making adjustments on the fly. We actually have to make decisions within 6 seconds before the shot goes through. And within 6 seconds, we're actually able to tell the cell if a good part is going to be produced or a bad part will be produced. So then the robotic can actually take that part and put it in a good bin or a reject bin. Okay, so there comes real-time process optimization on the cell itself by using some of these data parameters. Okay. After data collection, there is data evaluation. And I think an important message here is, you know, forming that data lake, that connected plant floor, it is not data just to be used for predictive analytics, which is our focus, but some of that data is also going into a traceability system because, you know, they are marking their casting parts, and, you know, if Audi or Daimler or GM, you know, recalls or there's a traceability question, a warranty question, they can actually use that same data lake to trace back those data parameters. So the message here is a standardized data lake, and that data can be evaluated by multiple systems, including predictive maintenance and predictive quality. Once that data is evaluated, collected, then evaluated, that data needs to be interpreted, okay? And there comes the people element, as James ended his presentation. So how to send the right information to the right person at the right time, right? So what's in it for you? So there's really 3 key roles that would interact with the system. And the folks at the die casting company, they actually set up a control room environment, which I'll show you on the next slide. But first, you have the process engineers, right? So they're able to visualize information in real time, okay? They're able to act based on process information that's being collected. Then you have the maintenance personnel who can see the health, they can receive predictive alerts, and they can act on the predictions and the diagnosis information. Then you have the maintenance folks that are responsible for the spare parts, okay, or even the spare part department, where they also get an understanding whether I need to, purchase a new bearing or a new motor or a new pump for my casting machine, and to find ways to reduce spare part on hand, which can be costly, and to predictively replenish spare parts when utilized from Bueller or from the maker of the die-cast cell, right? So again, the information should be interpreted and presented intuitively, and it should be presented to the right person in the right way at the right time. So the folks at the company actually ended up creating a control room, okay? Before I show you the control room, I want to show you two of the views that are used today by the maintenance and the process engineers. So on the right here, the process engineers could clearly visualize the health of the machine and the critical process parameters that are being collected. I mentioned there's more than 80 process parameters, but they always see the top 10, and they are ranked from the process parameter that may be unhealthy or leading to the issue on the machine. So in the case of cell number 2, which is running a Daimler product ID, the max pressure on the cell, is leading to a potential issue on the machine, which could lead to a defect. Where on cell number 1, the vacuum pressure of sensor number 3 or area number 3 could be the culprit here that is leading to a potential defect on a product ID, Daimler HR, et cetera, et cetera. So a process engineering view by cell, by product ID, and at the same time, an overall enterprise view where you see your factory, you see in this case a simple area with 2 casting cells, and under the 2 casting cells are the critical components of the cell. Of course, green meaning healthy, yellow means a degradation, and red means a potential failure imminent, right? So you can easily use your mouse, use a web browser, and then dive deeper into that asset to understand what process-related issues, maintenance-related issues, and quality-related issues may need to be taken to improve productivity and ultimately reduce the scrap rates on the machines. There comes then the control room, okay? So they really wanted to have everybody engaged, okay? And there was already an area in the factory where, vision data, camera data, and other areas, FLIR cameras and all that good stuff were being displayed, right, to the process engineers. So they further augmented that, and they actually started to include some of the predictive analytics, predictive maintenance, and predictive quality information also in the control room. So it becomes an area of collaboration, so that the people element with Industry 4.0 is taken care of, right? Everybody could collaborate and use the data to drive the ultimate reduction of scrap rates in the manufacturing facility, okay? So, moving on, I won't go through this, but I mean, there is an implementation framework behind all this, right? I mean, you have at the bottom here your machine layer, that's your casting machine, with the controllers, with sensors. You have data acquisition that's happening. You have the data flowing out into an application server somewhere. And again, folks on the call today, you might be using some of those logos that you see here. But the idea of predictive analytics at the end of the day is to be a complementary solution that could tap into your existing data lakes. And if the folks on the call are not collecting data today, there is an opportunity to create that data lake, to standardize it, and then to use it to start doing OEE, analytics, predictive maintenance, predictive quality, tools of the trade in order to drive uptime improvements and obviously to drive quality improvements. So to summarize, how are these things implemented, right? I'm just gonna go through the animation real quick, and I think the headline really summarizes it all, right? Think big. We want to improve uptime. We want to reduce scraps. Start small. We want to select 1 cell, 2 cells, and we want to pilot. We want to do what we call a proof of value, okay? We want to deploy a business case and an ROI in a specific area of the plant and scale fast. Based on this ROI, based on the technology deployment, create that template that can be rolled out to similar assets in similar plants fairly quickly, okay? Create your center of excellence within your manufacturing facility, your center of competence, who can then be trained on those technologies and can support the rollout of those technologies, okay? And that's the approach that we do follow together with our partners at Harvard, you know? Workshops, pilots, scalability using templates, okay? So, short summary from my side, and then I'll hand it to James. I mean, in our view, it is always very important to clearly strategize about your digital transformation journey, okay? Think big, start small. It is important to pilot these technologies and to keep the technology and the process and the people element in mind, okay? You know, technology is there. The technology is proven. The technology is used in companies that do casting and do many other applications, okay? It is just a matter of finding that business case that can be deployed in a phased approach to support the organization, to embrace these technologies, to use these technologies and to celebrate the wins, and then to learn from those wins and to replicate those wins across the organization. And James, I'd love for you also to give, you know, some concluding remarks here.
Yeah, so as Mo mentioned, it's like we have to leverage what we have today. If you really look at most companies, their CapEx spend is in the order of magnitude of, call it 5% in a given year. If that's the case, you could argue that you're going to have equipment that's going to be on your shop floor for 20 plus years. We can't go out and buy a bunch of brand new equipment and do this in one big bang, but we've got to start somewhere. We got to think big, but like Mo said, start small, and then use the incremental things that leverage other smart connected products to make that quote unquote dumb equipment that might be 10, 15 years old, to make it just a little bit smarter so it can help us do what we need to do. But we have to recognize that we've got to think about people, process, and technology. As Mo was talking through these control rooms, he was talking through, you know, look, this ties back to traceability. This ties back to other areas of our business. So we've got to make sure our processes are leveraging what we're doing so that the technology can be successful. And we've got to have the people trained to do that. So this is our call to action. We look at this in terms of manufacturing and Industry 4.0. It is no different than it's just a natural extension of operational excellence. We spent a lot of time today talking about quality and reliability, right, on the predictive maintenance side and predictive quality, but really it really spans the entire gambit. But this is, you know, what we focus on day in and day out. So this idea of going to implement Industry 4.0 and this roadmap, it can absolutely align 100% to the initiatives and the business planning activities that people already have underway today. And with that, we're going to conclude the webinar from a presentation perspective. Athena, we can open it up to questions, chats, or anything else.
Thanks, James and Mo. So as James said, we're going to open it up for questions. There are a number of ways that you can ask questions. Within the control panel that you have access to, there is a questions box. If you click within the questions box, type your question in and hit send, we will get that in on our end. The next thing that you can do is, if you are calling on a phone or if you have a mic set up, you can click that little hand icon. We will go ahead and unmute you and you can ask your question out loud. Last but not least, please feel free to reach out and email. James and Mo's email address are up on the screen right now. We can also email a copy of their email addresses, their contact information to each of the attendees today. So if you have any additional questions, you can reach out to them. So don't hesitate to do that. Maybe you can't think of anything right now, or you have to head out. Totally fine, but please know that they are a resource, and please feel free to ask them any questions that you might have. So with that, we're going to hang it out for a few minutes here and see if anything comes through. Again, chat is going to be, the question feature is going to be your best way to do that, unless you have a mic or you are calling in on a phone and would like to ask your question out loud. So we'll just hang out on the line for a few minutes here and see if anything comes through.
And I do recognize a few names on this attendee list. So if anybody, like I said, if anybody does want to email myself or Mo or call us separately, we kind of get it, but feel free to volunteer for being that first person. Well, Athena, do we want to call it? Doesn't look like we're getting any chats or questions in at this point.
Yeah, so if anybody is in the process of typing a question in that just hasn't come through yet, if you want to click that little hand icon, that'll just let us know that you're typing something in, and we should hang out on the line until something comes through.
I see a David White with his hands up.
Okay, so I think David is typing something in. I'll try to unmute you. Hold on one second. Hi, David, are you set up to take calls?
Yes, I am. Yes.
There you go. Do you want to ask a question out loud?
Sure. I'm curious as to how many suppliers in a die-cast cell have implemented the technology to allow you to gather the data you're requiring to be able to make the analytics worthwhile. We, for example, have in our furnace panels the ability to monitor a lot of aspects of what's going on with the furnace and send that information back to the customer as a report. But it also is available to be collected and put up, through a data collection system. I'm wondering if the trim press people and the robotic people, all of them, and the ladle people and other furnace companies have that same ability to allow you to acquisition or to access their data.
Yeah, David, this is Mo. I can start. It is a very valid question. I would say as long as a machine has a non-proprietary controller, like a Siemens or an Allen Bradley, most of the suppliers allowed us to get the data readily, including the casting machine suppliers like Bueller. I think the only difficulty we actually faced was with the robotic vendor. The ABB robots are a bit more strict through ABB, and there were some things there, but our client was able, if I would say, twist the elbows of ABB to provide us the data. So the client was quite supportive in their relationship with the supplier. So to answer your question, as long as there are, Ethernet capable controls available and, the relationship between the client and the supplier is there, we were able to get the data that we need fairly quickly.
Yeah, we do integration of cells also. We have a division called Delta Control that does that for us. So we can get in and do integration in an entire cell. And robotics are one of the toughest ones we face also in getting integrated. Now, you mentioned over the internet, one of the things that I talked about in my 4.0 presentation at the HPM symposium was you've got to have a great internet service. You've got to have a lot of bandwidth. You've got to have security if you're going to use the internet to do this. The other way to do it, of course, is over the Ethernet or direct cabling of everything that you've got in a cell into one central PLC that a program is written to be able to access the data and turn it into something that's usable.
Yeah,
that's actually
that's
what
the
we
piece
did.
that's probably the piece I glossed over a little bit, which was the infrastructure piece that you're describing. You know, people take it as a given, but it's anything but. And working through all those is a big deal. And to your point about the equipment, I mean, jumping over to the CNC side, I don't know if you do a lot of post-secondary machining, but we that really through like an MT Connect and other protocols, you can really pull a significant amount of information, pretty much everything you need off of a CNC machine, irrespective whether it's Makino, Haas, or whatever.
That's we're just getting into machining now because we're machining some ceramic board materials for the extruders and low pressure casters and people like that. And we're able to gather a lot of data off that CNC machine to make sure that what we're doing is within all of the tolerances that are required when you're machining, you know, particularly small parts. There's a lot of variables involved in die casting, and you mentioned you had, I think you said 48 different points or something like that that you're collecting, you know, with variables like die degradation and specific gravity of the aluminum and inclusions and plunger type fit to, you know, plunger failures or die spray. How are you monitoring all of that? I mean, is that possible to monitor that too?
Yeah, so in fact, we are getting about 80 parameters, 80. And I think just in short, you know, the trick is to dissect the critical equipment as part of the cells first, like you know, take the furnace, take the robot, take the trim press, and then to identify which variables, you know, correlate with which machine. So if you do it on a more component-based approach, then, you know, the templates can be deployed in a much more, in a better way. Yeah. That was the approach that we took. Yeah.
What we've tried to do is take the entire cell and take the data that we've collected, and if any part of the data comes out of spec, then we stop the robot from gathering the metal and we don't make the bad part. And I think that's what ultimately this all has to lead to, is that, yeah, you want to catch what the problem is, but you also want to stop the cell from making that bad part.
Sure.
So that when Toyota or Nissan or somebody comes back and says, hey, this part is defective, you can go back to your data and say, no, that day we didn't stop that cell. We didn't make an out of spec part. Let's put it that way.
Yeah.
You can still make a bad part further down the road with machining or whatever, but from a casting standpoint, it all starts there.
Yeah, and I think the idea is just to differentiate whether we're doing predictive maintenance or whether we're doing predictive quality. Because when it comes to predictive maintenance, we're looking at each component and the parameters within each component, like the furnace versus the robot. But when it comes to predictive quality, we're actually taking all the variables, all the 80 variables, and we're speccing them out, and we understand product tolerances of the variables. So there's also a product-to-product difference in the baseline and the template that is created on the cell, right?
Yeah, and we do the same thing with our furnaces with melters and holders. We can vary thermocouples in the lining and read temperature consistently, so that as the temperature starts to rise within the lining, we know that lining is getting thin or there's a crack in the lining. We can alert the customer that, hey, you may have a potential problem here. It's time to plan a shutdown to fix this. You know, we look at how they're utilizing the furnace, how often the doors are opened, you know, what kind of charging they're doing, and all this stuff is monitored so we can send them a report and help them better manage the furnace practices. You know, our tagline is, you can't make a good part with bad metal. So we're trying to constantly say, okay, this is how the furnace needs to be operated to get your best results. And then, you know, you look at degassing equipment and filtration and monitor temperatures on both sides of a filter to make sure that when it's becoming clogged, you can remove it. They even have, you know, equipment now that can give you instantaneous specific gravity on aluminum, which I think is going to be the next thing that we start to implement, where we can monitor, you know, basically what the density of the aluminum is. Are we getting the inclusions out? Are we getting the gas out of the metal too? So that you get the specific gravity you're looking for.
I mean, I can say a quick point on that. You know, the machine OEM or the supplier is actually critical. And one thing I forgot to mention is we're taking some of the analytics back to the machine maker, like Bueller, And in the future generations of the machine that they're shipping to greenfield facilities or whatever of our client or any client, they can actually have that data model ready on the machine. So when the new cell is deployed, the data is quickly available so that the predictive system can start working, right? Which is similar to the example you just mentioned, David. So I think at the end of the day, what we prove at the customer, there should be lessons learned that go to the machine OEM, the machine maker, to improve future generations of their machines.
Well, thank you, gentlemen. I think it was a great presentation, and I don't want to take up any more time in case somebody else has any questions.
Thank you, David.
Thanks, David. All right. I don't see any questions coming through, and I don't see any additional hands raised. And with respect to time, if you have any additional questions, please feel free to jot down the email addresses that are up on the screen right now. Again, you can always email us at NADCA, and we can put you in contact with either James or Mo as well. So with that, thank you guys for presenting today, and everybody else, thank you for attending, and we look forward to seeing you all on another webinar. Thanks, guys. Have a great day.
Thank you.
Thanks, everybody. Bye.
Thank you, James. Bye.